Hello, and welcome to the latest of our Twitch talks on new in version 12 features. My name is Itai Seggev. I'm a senior kernel developer here at Wolfram Research. If you've been following these talks, you may have seen me in a couple of previous talks on more mathy things like calculus and asymptotics, but today we'll be going at sort of the very opposite end of the Wolfram language and talking about some low-level operations, networking, and system operations. And so let me just give you sort of a brief overview before going into some of the examples. So here's our marketing page, and we have various features, and at the end of the features, there's a little link which will take you to a function page that gives you more details on how to do that. So for example, this create TCP and ZMQ servers. If you click on that, it'll take you to socket open, etc. And these are relatively low-level features. A lot of these are used by other features in the language. So if you've looked at blockchain or our chat server, those are built on top of these ZMQ things. Measuring things, the memory available, a lot of, machine learning algorithms require a lot of memory. So we have to carefully monitor how much memory we're using at one time, etc. So some of these you may never really need to call directly. Others may be more useful. But just a quick rundown. So we have some socket operations. We have ways of monitoring currently running processes. We have getting memory, capturing network packets, reading and writing byte array objects. That's something I'll go into a bit more depth. Processing text using the full range of Unicode characters, and I'll have to go into a bit more detail. And finally, WXF, an efficient binary format for serializing expressions to be consumed by other languages. And then we have several examples. You'll notice that they're in rows, which sort of follow the same order as the features. And we've tried each row to be sort of a coherent set. So we have sockety things on the first row. We have interacting with your hardware on the second row, and then more data-oriented stuff on the third row. And then a bunch of related functions. Some of these are new. Some are just very enhanced by this functionality, etc. And again, related guide pages. So these will be pages with lots of related functions for that particular functionality. And like I said, blockchain builds on top of this, cryptography builds on top of this, external system integration, the messaging interface, I believe, builds on top of this. So these are sort of core low-level technologies. All right, so let's just dig into some of these examples. So, and I'm going to use the click to copy feature to get started with these examples. So I can click to copy and paste this into my open notebook here. And apparently my Mathematica wasn't up to date, so now it is. And we get this socket object. We've created a sort of service. Then we connect to it. And so we get 3 more socket objects. And if we, you'll notice that this has a sort of a destination port, no source port. These have a source port. So these are things that connected to that destination port. And now we can do something like to each one of the clients, right? This is client number, whoops, I apparently did not actually click to copy. So to each client we're writing, this is client, and just putting in the number of the client. And now if we go to the server and ask for the, what is up with my click to copy? All right, and we, oh, we have 6. Oh, because I accidentally evaluated it twice. So it'll be interesting to see what happens now. And so now we read from each one of these connected clients. And I guess we'll need to abort this, and because we have, I guess I'll need to do this like this. Table read of connected of I for I goes from 1 to 3, and hopefully. Okay, so I have messed this up, so I'm just going to start over. I apologize for that. Slight copy and paste error, and then I got my clients and servers into an inconsistent state. So now we have 3. And so we can see that we got, this is client 1, this is client 2, this is client 3. And now we can just map close on across our clients to actually close the clients, and we can close the server to finish the example. So that's sort of a very, obviously a very boring example, but this is sort of the core technology. You set up some clients and servers, and you can, you know, have them communicating with each other. For a more advanced usage is to create a socket listener, which performs an action each time something happens on a socket. On a socket, excuse me. So I have set up this listener. It's listening on this port 7777, and each time something happens on that socket, it will execute this pure function, which will append to this variable called messages that we initialize to an empty list, and extract the data from the packet that was received, and go from there. So here's, again, we're just extracting the actual socket object from our listener. And now we're going to create a client that will connect to it. And now we're going to write a couple of messages to the client. And now our variable messages, which was an empty list, is now has 2 strings in it, which are the data from each one. And if I were to write another message, then write string client yet another message, then messages will now have been changed to be a 3 element. Right, and just to give you a sense of, well, actually, I guess I can't really do that without changing the listener, but it's documented sort of. So you notice that we extracted this, just the data. There's a whole association of information associated when something is written to the socket that is documented, and you can see what are the different fields you might want to extract. In this simple example, we just extracted the data itself. So we closed the client and then close the server. So these are sort of your very basic TCP sockets. It says so right there in the summary box that these are TCP sockets. We also have things called ZMQ sockets. And ZMQ is a high-performance framework, and it can use a variety of different low-level sockets. So we might call this a sort of middleware. This is the technology that underlies the Wolfram chat service. And so we don't care about the port, so we just said automatic, but we want this, rather than being a raw TCP socket, to be a ZMQ socket, in particular what's called a ZMQ pair, because we're going to need two connected sockets, which are sort of exclusively connected to each other. So socket B is created as a connection to socket A. And now if we write to A and then B, then we will see that the message will appear on the opposite socket. And so socket read will extract the message as a bunch of bytes, because you might be sending raw binary data, and so we're going to convert that to a string in this case. And so socket A received the message, this is from socket B, and socket B received the message, this is a message from socket A. So that's just illustrating the basic functionality of 0MQ. What's perhaps more interesting is the publish-subscribe model, where you can have multiple things connect to a single server that sort of pushes things out to all of them. And so here we're going to create a publisher, and then we'll have a bunch of subscribers. And again, the syntax is very similar. We're socket connecting to the destination port of the publisher, and we're just saying that we're a ZMQ subscriber rather than a ZMQ publisher. This is what makes it a many-to-one instead of an exclusive pair. And so now we can we can have each one of the subscribers subscribe to all publishers on the publisher. And then we write something to the publisher socket, and that message will appear on all of the subscribers. And so this is a way of, having something like a push service model implemented. Okay, so that's sort of networking. Now to something slightly more more local, your machine. We have a memory available, which is, the concept of memory available is a very fluid concept, depending on your operating system and in fact, your operating system settings. But this is sort of, if you were trying to allocate a bunch of memory for some data, this is, sort of our best guess as what you could easily get without, causing the operating system to start swapping or pushing around memory, etc. So apparently I have about 11 gigabytes. We also have, if we open system information, we have a new tab in the system information called machine. So memory, I guess it's so this should correspond to that. So I guess it's actually more like 10.6 gigabytes. I have 32 gigs of RAM on this machine, et cetera, et cetera. And the system specific, so these are sort of available on all platforms, have roughly the same, more or less the same concept. Then we have operating system specific information, wired versus active versus inactive on Windows. I'm not a Windows expert, and so the names on Windows suddenly are just escaped my mind. I apologize for that, but on Windows and on Linux, you'd see slightly different information with slightly different names. And of course, like all system information, you can get that by, just that tab, by getting system information of machine. If you want to extract a particular value, you can do that. And then here's sort of a neat example, which I'm not going to go through all of the details of it, but it gives you a nice, it's like your own system monitor of the available memory. And right, basically we just, we take, we're looking at the physical memory used and sort of dynamically updating that over time. Okay, so that's system memory. Then we have system processes, and I shudder to think what this is going to show. But let's look for all processes which match the name Wolfram kernel, and there are 8 of them, which you basically have 2 kernels open every time you open a front end. Because you have the kernel that you're using and then the kernel that's used exclusively by the front end for giving user assistance and whatnot. So I probably have 3 or so front ends open, and some of them have a couple of kernels, user kernels connected to them. Now, you can sort of make various queries, and the documentation goes into the details of this, but here we're going to look for processes with many threads. So Firefox has a bunch of threads, Eclipse has a bunch of threads, plugin container, I'm guessing this is something, yeah, from Firefox. And then, you can again, query various information from these process objects. For example, so you can ask the name of the program. And okay, so whoops, I did not actually copy that. Now let's extract all system processes and then take the 5 programs using the most memory. So Eclipse, Firefox, then but Zoom, which I'm using to share my screen, and WebKit, which is probably the my Twitch session is apparently using up a respectable amount of memory at the moment. All right, so that's local machines. Network packets. So so we have a couple of that was interesting. Couple of functions that look at network packets, and I tried this and it fails, and it says unable to read from network interfaces, requires read permissions for device dev BPF star. So operating systems don't allow just anybody to walk around and inspect for all packets as opposed to just the packets headed for them, because that's an obvious security concern. So you have a couple of options. You can run as root or administrator, depending on your platform, or you can reconfigure your OS to allow certain users to read directly from the sockets. I'm essentially going to do number 2, only rather than doing it on bare metal, I'm going to do it on my nice isolated Linux virtual machine here, so that you're not, I'm not opening myself up to random attacks. So, so network packet capture with no arguments gives you this little interface here, and then you can press record. And ooh, that is interesting. Why did that fail? Okay, random failure. And you can pause it, or you can just end it. When you click end, It'll think for a little bit as it takes all that data and creates a data set out of it. And hopefully I will get an answer soon. Wow. I did not expect that to... Okay, let's see if we can interrupt that. All right, let's see if I just record for a shorter period of time, if it will, or if I'm now in a... Here. Well, no, I can't do it that way. So I will try this one more time, and if this doesn't work, then I will apologize for my slightly non-functional machine. And are we running out of memory because this is a virtual machine? No, we have... Oh, there we go. So just a little bit slow creating the data set. Because, like I said, this is a virtual machine, so it's not as powerful. It doesn't have nearly as much RAM as the host machine. So we see we get a lot of packets, different destination ports. So apparently, port 22 is SSH. So apparently, I've SSH'd into on the local interface. Yes, that's true. I did SSH from one machine to another machine, and yeah, 17,487 packets were recorded during that very brief recording, which is why it took a while for this to format. So that's network packet capture. It creates a pretty interface for you to record things with. Network packet recording, you give it a time, and you can, well, here, let me show you actually just what happens if you do the one argument form. So with the one argument form, and I'm only going to record for, say, 0.1 seconds, and apparently I didn't record anything in that time. Let's give it half a second. And we get a bunch of packets out, 150. So that with network packet, so network packet capture gives you an interface to record things with. Network packet recording, you give it amount of time, and it records all packets during that time. And you can specify things like only give me packets on this interface, only give me packets that are connecting to involve point 443, which is HTTPS. And so I'm going to record for a couple of seconds, and it tells me nothing because I don't have any current connections on my Ethernet port connecting to point 443. Now with network packet trace, that takes an expression to evaluate, and it records all the packets which occurred during the evaluation of that expression. So, whoops, and I want to copy this restriction here. And so I'm going to use URL execute to connect to an HTTPS location. So obviously, I'm now going to have HTTPS packets that will be recorded during this trace. So those are our three functions: network packet capture, network packet recording, and network packet trace. Let's see, is there anything else I wanted to tell you about these guys? I don't think so. So I will move this out of the way. And yeah, so I showed you, right. And I guess I didn't highlight, so I will bring it back and just show it. So we have $network interfaces, which tells you what are all of the available interfaces. So since this is a simple virtual machine, there are 2 of them, on your Windows machine, or even on something with bare metal, you might have a bunch of interfaces running around. Okay. All right. Read files directly as a byte array. So let's walk through this example because it's a neat example. So we have this GIF file in our example data directory. So you can just open read byte array and read it as a bunch of bytes. Now, if we take the first 6 bytes and read them as ISO-Latin 1 characters, then we get the string GIF89. So every GIF, at least, well, I suppose it might start as be GIF87 if it's an older GIF, but starts with the characters that spell out GIF89A, etc. So the next 4 bytes, so here I'm looking at byte 7, 8, 9, and 10, they encode the dimensions of the image as 2 16-bit integers. So if we import this byte array, i.e. convert this blob of bytes into an expression, which will be an image. So let's do this actually in 2 steps, right? So if I import the byte array, it turns it as an image. And then I ask about its image dimensions. Look, it matches what was in the raw encoding. If we, there are other operations you can do with byte arrays, such as base encoding them. So here's the short version of the base encoding. Yes, base encoding gives you, is less efficient than just raw. Ooh. Oh, I guess I did that. What just happened there? That's what happened there. So it's because base encoding uses, well, your basic base 64 encoding uses 4 characters or 4 bytes to encode 3 bytes of data. So it's 4/3 larger, but you don't have any sort of special characters in it. So back in the olden days when you were worried about being 7-bit clean or 8-bit clean, that was a very important consideration. And of course, the advantage of the reading directly into a byte array as opposed to just using read list and then converting to a byte array is that you save a factor of 8 of memory on a 64-bit machine, a factor of 4 of memory on a 32-bit machine. Another thing that's quite neat about this is you can use different terminators. So here I've opened a connection to our example data server, and I'm going to write to that socket a raw HTTP a raw HTTP command. And I'm going to encode this GIF89A as a byte array. And the reason I'm doing that is because one of the second argument to read byte array is a terminator, which can be end of line, it can be end of file, it can be a bunch of normal, but it can also be a byte sequence to stop at. So if we we read until we see the start of a GIF89, and what we get out is, and actually maybe I should just take off take off the short here. So So if I now convert this byte array to a string, then I see a bunch of HTTP headers. The server content type tells me that it's going to be an image GIF. So now I'm going to read the remaining data off of the socket. And I'm going to join that with the Terminator, which we already read past, and import it as a GIF. And we see we get a bunch of GIF images. So that's sort of a very powerful way to use read byte array. Finally, full range of Unicode characters. So I guess I need to be sort of clear on exactly what this means. We've long had, if you are expert in them, a way to type in 2-byte characters and 4-byte characters. Sorry, 1-byte and 2-byte characters. So these are 2 hex digits. So this is a 1-byte character, which once we evaluate it, you'll see is the letter A. This is a Hebrew shin. This is a Chinese character whose name I don't know. But what we've added is a way to type in 3-byte characters because if we extend to the full range of Unicode, which is a 21-bit standard, then we can have up to 3 bytes per character. And we evaluate this and we see an A, the Hebrew shin, the Chinese character, and the crying tears of joy emoji. And why did I choose these characters? Well, if we look at their character codes and then and how they look in base 16, one uses two 16 digits, one uses 3 16 digits, one uses 4 16 digits, and one uses more than 4 16 digits. And the reason that's important is because if you encode things as UTF-8, each one of those sizes will require a different number of bytes to encode. And so string to byte array, unlike 2-character code, because you can't have character codes larger than, because there are in fact character codes larger than 1 byte, defaults to UTF-8. So these 4 characters became 10 bytes, and I've split them into 1, 2, 3, and 4 bytes. And if I convert them back to characters by mapping byte array to string across them, then I see the first byte is the first character, the next 2 bytes are the next 2 characters, the next 3 bytes are the third character, which was the highest number of bytes you could need in versions prior to 12. And then the last character required 4 bytes. And so now things aren't perfect. As you can see, there's this extra space between the emoji and the closing brace. And actually, if you try to cursor through, you can actually be in the middle of the emoji and sort of delete half of the emoji, which is an unfortunate side effect. And that's because, well, if you know what UTF-16 looks like, then it's because the underlying representation is UTF-16, and the front end isn't, it understands UTF-16, but it doesn't sort of fully understand all of the consequences of how to render and cursor through those things. So from a kernel perspective, you can process these characters, do whatever string operations and byte operations you want on them. If you display them in the front end, you may find, or try to edit them in the front end, you may find slight glitches. And it's certainly something we're working on improving, but it'll be a long process for all sorts of complicated technical reasons I don't want to go into. Okay, so that's Unicode characters. And then our last example is WXF. This was experimental in 11.1, 11.2. We tweaked it, improved it. And it's basically a way to sort of encode things in a as a bunch of bytes in an easy to read fashion. So here I have a bunch of expressions. I can call binary serialize, that turns them into a bunch of bytes. If I deserialize those bytes, then they become, they're equal to the expressions. You can use export to right, and I use the WXF extension here on the file to automatically select the format. You can write them out, and what was written out is exactly equal to what binary serialize returned. And similarly, if you were to import this file, you would get the original expressions. And what's important about this is that this is sort of a documented format. So if I go to the documentation that's linked to from there, then there's a sort of detailed description of the format. So we've written already a converter for Python. I think we might be working on converters for more. If somebody on the Zoom session knows the answer, please Zoom chat that to me. But I think we've certainly done Python, and we may do more. We're also working on sort of open sourcing. We have one for Java. Thank you. We may open source. It's that requires some engineering review, some legal review. So exactly when and if that'll happen, I can't say, but it's certainly something we'd like to do, have a reference implementation for people to use. So there's that's WXF in a nutshell. All right, Java and C, C++, right, which is sort of the core implementation. All right, so let me see if I think it seems like memory pressure for FE versus running subkernels. Yeah, so obviously if you run, so I'm just looking here at some questions that appeared on the Twitch chat. So there was a question about memory pressure for FE versus the subkernels. So it won't specifically tell you the memory pressure from the front end. Of course, you can use system process data to locate your front end and get information that way. I mean, what the memory things mostly tell you is, memory available tells you how much memory is available for any process. Now, so if you were to run that into a subkernel, then it would know how much memory is available for that subkernel, but it wouldn't necessarily be aware of the fact that there are other subkernels. It's a little bit fuzzy what exactly that would mean, but that's maybe, something we can look at and see if we can answer something out. Let's see. Yeah, we don't have, so this was answered in the Twitch chat. GPU memory, sensors, and disk space. We do not have those. Those seem like, certainly the disk space and maybe GPU memory seem like pretty good, pretty obvious suggestions that we could look at. GPU and sensors, that's, I mean, that that varies a lot from system to system. So the reward, the return, the reward on effort is not nearly as clear. And with GPUs, I mean, GPUs are very sensitive beasts. If you write to them or in the wrong way, you can very easily crash your machine. So I would be, sort of very, very, very gentle in what we do that. But it's certainly something we can consider. Um, um, and see, there was a question about the random dollar failure network packet capture. That's a good question. I think it's well, we've made sort of a couple of tweaks to package loading and dynamics, which may or may not be related to that. It's not an easy problem, or we would have figured it out and fixed it by now. It's most likely sort of two synchronous evaluations competing with each other. So I'm not sure I have a great answer even for how to proceed. But perhaps if if I think of something, I'll maybe send something out on Stack Exchange or some place where people can see it. And then, just since this is mentioned on the live stream, if you started a cell with a greater than sign, you get these Python cells. So, well, that's probably a stupid one. Abs of -2. And you evaluate, then this goes out to Python and evaluates it and then accepts the input. And so in version 12, we have Python and Node.js. We're adding a bunch more in version 12.1, like Julia. And if my elf wants to tell me what are some of the other languages. And we're sort of refactoring sort of how this drop down works, so it can sort of be dynamically updated. So as we, add new languages, or if you perhaps someday, if you create your own link, you'll be able to add it here. Right, I see Todd has answered on Twitch that Julia, Ruby, R, and Tickle have been added for 12.1. And right. So I will give, I'll pause now for 30 seconds to see if any last minute questions arise on the Twitch chat. About storing it in variable, it's perhaps not quite as nice, but you can, so there's a question about how to store in a Mathematica variable. Well, you can always use the external evaluate command itself. Python abs of -2. And so now x is equal to 2. Exactly how you do that in a Python cell. Right, and I see. Yeah, so that's that's maybe something worth thinking about, maybe using external. I mean, we do have external identifier, external function, so maybe there's some way to make that work. But yeah, as of right now, I think these are your two options, referencing %77 or using the external evaluate command and storing it in a variable. Okay, so that seems to be all the questions. So thank you very much for spending these 45 minutes of your life with us. And I hope you have been enjoying and will continue to enjoy using version 12 of the Wolfram language. Thanks. Bye.